Alright, now we're going to look at an example of a problem where we have diffraction caused by a single slit. So this is example 6, and this is found on page 868 in your book if you would like to follow along. So in this example we have light passing through a slit and it shines on a flat screen that's located 0.4 meters away. So it's telling you that that's your value for L. So we could go ahead and record that here. L equals 0.40 meters. And again, that's the distance between the slit and the screen that it's shining on. Okay, the wavelength of the light in a vacuum is 410 nanometers. So wavelength equals 410 nanometers. The distance between the midpoint of the central bright fringe and the first dark fringe is y. So let's draw a little diagram so we can see what they're talking about. So if this is our slit where our light is coming through, and this is our screen over here, this would be the midpoint of the central bright fringe directly across from the middle of the slit. And then let's say up here this is our first dark fringe. So this would be dark here, and this would be bright. So they're calling this distance y. This is the same distance that we've been calling xm. So it doesn't really matter what we call it. Okay, so we're supposed to determine the width to y of the central bright fringe. So this dark spot here is mirrored by another dark spot on the other side. So the same thing that's happening with destructive interference in this direction is also happening with the waves that are spreading out in this direction. So what they want to find really is the width of the central bright fringe, and they're telling us that's going to be 2y, or in our case 2xm. So that's what we're really trying to find. So if we can find this value xm, then we just need to double it, and that will give us the entire width of the bright band. So we're supposed to do this for two different cases. First of all, for A, when the width of the slit is 5 times 10 to the negative 6 meters. So in our equation, that's what we've been calling D, 5.0 times 10 to the negative 6 meters. Okay, so we could use either D sine theta equals m times lambda, and then we could solve for the angle and then use trigonometry to calculate this side, and that's the way the book does it. However, we could just go ahead and use this approximation. xm is approximately equal to m times lambda times L over D. And we can be fairly sure that this approximation is okay in this case because our screen is 0.4 meters away and our slit is very, very small. So it's likely that we're going to get a bright fringe here that's much smaller than 0.4 meters. And so this approximation will be okay. So if we can find xm, then we just need to double it to find the width of the bright fringe. So we're looking for the first dark fringe here, so our m would be 1. Our wavelength is given 410 nanometers. Our L is given as 0.4 meters. And then our D for part A was 5.0 times 10 to the negative 6 meters. So don't forget when you're typing this into your calculator, this nano stands for 10 to the negative 9th. So this is really 410 times 10 to the negative 9th meters. So if you type that all in, you get xm is equal to, what did I have? 0.033. So then if we double that, 2xm to get the entire width of the bright band, not just from the center to the edge, but from one edge to the other, that's just going to be double that. So 0.066 meters. That was meters as well. So then we can verify that our approximation here was okay. This is 0.066 meters. That's much, much smaller than this distance here, which was 0.4 meters. So I want you now to try part B. So part B, everything is the same except now the width of the slit is 2.5 times 10 to the negative 6 meters. So again, that would be our D. Okay, so pause this for a second, try part B on your own, and then turn this back on to see the answer. Okay, so there was a couple ways that you could have done part D. One way would have been to just use this equation again, plug in all these values again, and then down here plug in your 2.5 times 10 to the negative 6 meters. And that would be perfectly fine. Another way would be to notice that this width is exactly half of what our first width was. And we're dividing by that number. So we're dividing by a number that's exactly half as big as the one we did before. So that means our answer should be twice as big as it was before. And if we plug all of the numbers in here to verify, we find that that's true. So we get a value for 2xm for part B of about 0.13 meters. So that's pretty much double what this was before. Alright, so after this video, I would like you to try page 884 at the end of the chapter and try numbers 19, 21, and 22. Those will be good examples of using these equations with single slit diffraction.